So this next hour, let me load up the schedule, will be kind of taking what we've learned so far about kind of what goes into building Miniscopes, how to get Miniscopes, your surgeries working, implant a GRIN lens or a similar type of surgery. You could do a cranial window. And now Federico will do the first half of this talk, and he'll go over how you actually build a Miniscope. So how do you end up building something that can image through the optical implant surgeries that we just watched from Tristan and Susie. Then maybe we'll have a bit of time for some questions, and then I'll go through, once that's built, how do we kind of actually start streaming data to the computer? What does our software look like, and what are some of the features for it? I'll just highlight as well, like oftentimes people getting into using Miniscopes feel like building Miniscopes is going to be a really difficult. Maybe you've never soldered anything, even though you can now completely avoid needing to solder anything, or maybe you've never handled any lenses before. But it's really hard to break any of these components. And while there are options through OpenEther's production site and LabMaker to buy fully assembled systems, I really like the idea, when possible, for you to get assembly kits. So you can source all these components yourself, but you can also just buy a kit, which ends up costing less than trying to source it yourself through OEPS. And then it might take you, for us, we can probably build a Miniscope in 15 minutes, but for your first time, it might take you hours or days to put it together. But investing that time is really worth it, because once you've built it, you're not afraid of holding it and using the system anymore. And if something breaks in the middle of your recording, you can jump right in and fix it. And it's I think really empowering to kind of get yourself into building the systems. And again, the time commitment might be more than 10 minutes initially, but once you've built one, you can build 100. And that's also really great. So anyways, I will stop there, and Federico can share a screen and go over cable and Miniscope assembly.
Sure. Okay. Okay. Do you see my PowerPoints?
Yep.
Perfect. So as Daniel mentioned before, my name is Rico. I'm going to be showing how to assemble first the coaxial cable using the Miniscope, and then assembling the whole Miniscope. Okay, so at first, what I would like to show is which tools I use for assembling the Miniscopes on the cable. So to assemble the cable, what I use to cut the cable is a scalpel. This makes things much easier to cut and to open. I don't recommend using a cable stripper because of how the coaxial cable is assembled. Then to solder things, I use a Flux. I use Flux with a dispensing syringe. Flux comes in very different kind of ways. You can also use the Flux in a pen, but I prefer to use the syringe because it allows me to put the right amount of flux in the surfaces I want to solder. And then some forceps for assembling this. The coaxial cable is any forceps is okay. And then some tools that are recommended to use also is a stereoscope. The size of the cable is very small, and the connector is also very small. So trying to use a magnifying glass is not ideal. And to solder things, we need a soldering station and solder. So the first step I usually do is I solder the SMA connector, the cable to the SMA connector. The kit, the coaxial cable kit, I had already the PCB soldered to the SMA connector. It may come separate, but the solder is very easy. It's just soldering the paths to the corresponding pins. So before starting, it's a good idea to see how the PCB and how the SMA connector looks like. So this is this is the ground path where we have to solder the ground of the cable, and the connector in the middle is going to be the data pin. All of the other connector, all of the other pins, for example, this one and this one, are all grounds. So the first step is removing the protection of the cable. And for this, what I do is I will stop here for a second. I put the cable on the SMA connector, and I just measure roughly where I want to cut. I just make a small dent, so I know exactly which length I need to cut. Once I know how long my cable needs to be, I just remove the first part of the cable, which is the white insulation. So to do this, what I do is I put this cable on the cable, and I just roll the cable a little bit, and then the cable will just cut itself. And with the forceps, I just remove the protection. So now we can see that the shielding, which is the ground, is exposed. This the next step is to pull back that metallic shielding and keep it as compact as possible, because we need to solder it here on this path. So what I do is I grab with one forceps to one end of the cable, and I just pull the metallic shield to the other side. And usually that keeps things very compact. If it doesn't, you just can push the shielding a little bit, like I'm doing now, and it will be just fine. It doesn't need to be perfect. This will be covered in solder, but keeping it as compact as possible is the best idea. So the next step is to remove the second insulation, which protects the inner connector of the coaxial cable. The procedure is very similar to the first one, which is placing the cable on the PCB and measure roughly the length of the sensor connector. By doing that, it's much easier to remove the connector outside the PCB. So what we do is we make a mark, and then we just roll the cable just a little bit, and that will cut the insulation. So if you can see, the cable is like bent here, so that means that the insulation is broken, but the cable in the connector in the sensor it's fine. So with a forceps, we have to be very careful to remove it, and there is removed. So here we can see the shielding, which is the ground, is connected to the sensor pad, and then the rest of the connector is aligned to the sensor pin, which is where is the data pin. So we will pull it back a little bit more, just to keep it compact again, and there is fine. So the next step is adding flux to the sensor pad and to the connector in the sensor. This will make solder much easier and much cleaner too. So first we solder the ground pad just to keep the cable in position, and then we just solder the inner connector to the sensor pin with the same procedure. And then this side of the cable is ready. So the second part of the cable is connecting the UFL connector, which stands for micro FL. So this is the part that goes into the Miniscope. It's highly recommended to do this under the stereoscope, because this part is very, very small, and this pin needs, and it's very important to keep this pin as isolated from the rest of the body of the connector. So as we did before, we place the cable close to the connector, and we make a mark where we want with the length of the shielding that we want to leave. So what I usually do is when I cut this, I just make sure that I have enough shielding to solder on the microFL connector. And then I have a small part that protrudes here. So I can remove the shielding, I can remove the second protector, and leave the inner connector uncovered. So as before, we pull the metallic shielding back, and we expose the inner connect. We expose the second protector. We cut again with a scalpel just a little bit of the second protector to leave the inner connector exposed. We remove it, and then we see that everything is right in place. So now we add some flux to the, so I'm going to stop here for a second. We add a drop of flux on this part of the connector, which is going to be the ground. And we have to put a very tiny drop of flux on the smaller pad. This is going to be the ground, and this is going to be where the data pin is going to be connected. Now we add just a drop of solder. It's a good idea to hold the microFL connector with some tweezers or forceps so it doesn't move around. Just a little more, and we put a little bit of solder on the small pad. Now we add again flux to the inner connector and to the center pin. We put it back on in place. And we solder the shielding to the body. So once the shielding is connected to the body, now we can solder the data pin, which is going to happen now. So we put some solder on the soldering tip, and the cable is fully ready. So the first time people do this cable, it may take a long time, which is fine. Just make sure that all the lengths are everything is connected correctly and nothing is shorted. So for assembling the Miniscope, we need some other tools. So what we need is a T2 torque screwdriver for the screws that are included in the kit. We need some lens clean tissue, and we are going to use this for two purposes. First, to clean all the surfaces that we may get dirt on, and to protect the lens when we're going to push them into a surface. Cotton swabs and plastic, and I prefer to use plastic tweezers so I don't scratch the surfaces of my filters and my lenses. And for gluing the Miniscope, there are two options. You can either use a two-part epoxy or UV glue and a gun. I prefer to use the UV glue, and my choice is usually Norland 68. It's one of the UV glue from Edmund Optics, and it works great for this. So this is so first I want to show like an exploded view of the Miniscope. These are all the parts of the Miniscope, and all of the orientation of the lenses and the filters are correct to what they should be on the Miniscope. This diagram can be found in our wiki in GitHub. And it's important to notice that you need to have every single part before assembling the Miniscope. So just make sure that everything is there when you're going to assemble it. So one recommendation I can give is use gloves to do the whole assembly. How the surface, all of the working surfaces have to be clean. And the first time you do a Miniscope, please take your time. So the first thing we are going to assemble is the objective, which what we need for this step is the objective module, 2 3mm diameter lenses. For this tutorial, I'm going to assemble the standard objective, but these lenses can also have different focal lengths to achieve different field of view and working distances. And it's very important to notice that the lenses have an orientation. So in this case, the flatter surface will have to face the bottom of the miniscope. So in this video, I show how I insert the lenses. So the first thing you have to do is place one of the lenses on a hard surface, protected with some lens tissue, and then just push the objective into the lens. Before inserting the second lens, what I usually do is check the orientation of the lens, just in case I made a mistake, and then I just push the second one in the same procedure. This step of inserting the screws is optional, but it's highly recommended because it's going to make the assembly easier in a later step. The screws have to be very loose. They don't have to protrude the holes. They have to just be in position. The second thing the second step is going to be assembling the excitation module, which this one is very easy to assemble. It's just the excitation module and the excitation filter. I left the part numbers in the explored view just to make sure that everything is in the right position. If you swap the lenses, the Miniscope is not going to work correctly. A very important thing to notice in this step is that filters have they also have an orientation. So they have a coated surface, and and that should face where the light is coming from. The filters we use come from we purchase them from Chroma, and they include an arrow that faces the coated surface. Be careful, this is not always true, so always check which coated surface, which one is the coated surface. The procedure is very simple. It's just, so this is a very good example. This is the coated surface of the filter, and you will notice that it looks like a mirror. So what we do is we just grab the filter with, so here you can see the arrow pointing the coated surface, but just be careful that sometimes this arrow can be wrong, so always double check. And I use the plastic tweezers to grab the filter. I insert it in the pocket, and it may not fit exactly on the pocket, and that's fine. So the way of inserting the filter to the pocket is just to use a cotton swab and push on the edges of the filter, and it's just going to enter. That's okay. And just finish pushing it down, and the excitation module is ready. The third step is to assemble the emission module. And for this, we are going to insert the 4mm lens and the dichroic mirror. Please be careful also. Please also be careful that the 4mm lens has an orientation. In this case, the rounded surface faces to the bottom of the module. Also, the dichroic mirror has an orientation too. The coated surface has to face the hole where the half-wall lens is. So we can see it here that if you see the arrow and you see the coated surface here, the hole of the half-wall lens is right here. Another way that this can be explained is this this screw faces in the opposite direction of the coated surface. The assembly for this step is it's also very similar to the objective. So place the lens on a hard surface covered with some lens tissue. Grab the excitation module and just push down. It will not fully go in because the surface is not going to be completely, it's going to be flat. So now just grab the cotton swab and just push it the remainder of the lens. It may be a little stiff, so just push and it will just go in. And here you can see that it's perfectly flat. I usually check that the orientation is correct. If it doesn't, now is the step to just remove the lens from the top. And now we are inserting the dichroic mirror. Again, use some plastic tweezers so you don't scratch the surface of the dichroic mirror. And there it's in place. So now we bring the excitation module we assembled in the step before, and we place the half ball lens that is right here into the bucket. So here I show the part number, which is included on all of the kits for assembling Miniscope. And this part can be a little tricky. Just inserting the half ball lens in position just works because then the excitation module will just put everything in place. And then we just put the excitation module in. Once everything is in position, we just screw we just screw the two parts together, and this part will be ready. So I'm going to push forward a little bit. So this step is just screwing just putting the screws. This part may take a bit of time just to screw the things. So take your time and don't bend, don't push too hard if it doesn't fit. Just go slowly. I include this step as a separate step because it gave some issues in the past, so it's worth mentioning how to properly bend the cable. The electrotunable lens cable has these two contacts, which the correct way of bending this is to sandwich this. The lens has to be sandwiched here. So the correct way of bending is taking this connector and just bring it here, like I'm going to show in this video. And please be gentle. This cable is very very flexible, so it doesn't need a lot of force to bend the cable, and like that it's fine. So this is this is the hardest step, and this is the one that this usually take more time to do it, which is joining together the objective and the emission module. So the very first thing that is important to notice is which is the orientation of the electrotunable lens. So the electrotunable lens has these rings on what we use as a top, and this is the correct orientation of the electrotunable lens. Also, to make things easier, make sure that the screws are not fully threaded. So when you join things together, they can be perfectly flat and you can just screw them correctly. So this step, which I have a lot of experience and I do it very fast, takes a lot of time. So take your time to place the lens with the right orientation. Then insert the electrotunable lens cable. You may flip the lens a few times here, it's fine, just put the lens back on. So once the lens is fully in, just put the emission module on top. And with the screws that you place in the first step in the objective module, just join the mission module with the mission module. So I'm going to stop here for a second. I don't know if you noticed that the bending of the cable looks a bit off. That's fine for now. So before screwing the screws all the way in, just make sure to put the cable on the right orientation so it fits the excitation module. This is something I'm going to show in the next step. Yeah, so here what I do is I just accommodate a little bit more the electrical lens cable, and I finish screwing the screws in. Again, take your time to do this step, and if things don't fit, just start again. This is completely fine. Yeah, so this is just screwing the three screws in place. So now the step we are missing is screwing the excitation module to the the excitation PCB to the excitation module. One thing I prefer to do is putting the screws before joining the two parts together, so it's easier than to just screw them in place. So this step is just basically screwing the excitation PCB to the excitation module. So now we have to put the final filter that we are missing. That is the emission filter. And again, this filter has an orientation, and the coated side has to face down. So if following the arrow should face down. So the coated surface should be here. So here in this step, the only thing we do is place the filter in place. Also, if the filter doesn't fit perfectly on the hole, just push it with the cotton swab, and it's going to fit right in. So only once the filter is in place and everything is fine, only then just remove the protective tape from the image sensor. Sorry, I don't know. And removing the tape is just peeling it off, very simple. And then close the Miniscope. So one thing I like to do before gluing things, so now the Miniscope is ready to be glued. One thing I like to do in this step is I like to connect the Miniscope to my computer and check if there is any dust or anything that doesn't look fine. It may happen that some dust or particles get into either the emission filter or the image sensor. So this is the perfect time to clean both surfaces. What I do to clean the surfaces is just use isopropyl alcohol with a cotton swab to just leave the surface really clean, and then I use the lens tissue to just remove any kind of anything that may be on any of both surfaces. And now the final step is just gluing the PCB to the emission module. So what I do is to put the right amount of glue, I take a cotton swab and I make like a little spear with like a very pointy, so I can put just the right amount of glue. Don't put an excess of glue because then it may get into the emission module, to the emission filter, and will just block the field of view. And something very important is don't rush and do one side at a time. So here I start with this side, which is the easiest because I don't have any PCB there obstructing. And then I just, with my UV gun, I just cure the UV glue. So in doing this whole process, I keep the Miniscope upside down and I just keep it closed with my fingers. This is important. That's why it's important to use gloves, so neither surface either gets dirty or damaged. And now I just continue with the rest of the sides. And the final side. And then the Miniscope assembly is ready. So a more detailed guide can be found in the wiki of our GitHub, and any other questions can be made in our Miniscope Google group. Yeah, that's it. I don't know if I have time for any questions, but I hope this helps.
Thanks a lot, Federico. I tried to answer as many questions that were coming up in the chat. I think I got all of them. And if people have any questions, they can type in there or raise their hand.
Yeah, sorry, I didn't see any questions. I had a full screen, so I didn't see any questions. But I have a breakout room just for this, so feel free to join.
That's good. And again, as I mentioned, it can be intimidating, like doing it your first time or watching these videos and thinking that, oh, it's so hard. It's, again, really hard to actually break any of these things. And once you go through it once, then you can build a million of them. Also, I'll mention, like, the biggest, some people are afraid of soldering. And as Federico showed, the thin connectors, they take, a little bit of skill and practice to solder properly. So you can also just buy from, I think, LabMaker and OEPS, a fully assembled coax cable if you don't want to deal with it yourself. But being able to do it means that if something breaks in the middle of the experiment, you can easily fix it.
Yeah, also in my experience, at first, it was very hard for me to do the coaxial cables, but once I learned how to cut them with this cable, they were very easy. And what I see is that coaxial cables, they may break often, just because the mouse bites them or things are out of our control. And being able to just cut the coaxial cable and replace and just fix it, it's very valuable.
Okay, cool. So I will now go over, now that we have an implanted mouse, we've built our Miniscope. What's the next step in getting things connected and streaming and collecting data. So I'm going to attempt to not do a PowerPoint talk and do all this live. So we'll see how this goes. So let me share my screen. And again, if you have more assembly questions later on, you can join Federico. I mean, probably any of the breakout rooms are people experience doing this. And okay, cool. So we're going to go over kind of setting up the Miniscope software, streaming data, collecting data. Even if you're using a version 3 Miniscope and maybe have kind of been using it for a few years and really committed to the older software, I would like to emphasize that this newer version of the software, which now has been out for since the version 4 was released, and we try to kind of maintain it and add features, is more stable, robust. So you really consider switching over to it when you can. And this supports all previous devices, all current devices under development as well. Okay, so the first thing is if we want to get our software, there's links on miniscope.org, which will take you to the GitHub repository of the Miniscope acquisition software. And here you can clone the actual source code, you can download it, you can compile it yourself. But really what most people want to do is just use it. So if you go to over on the side, there's this little release area where every time we make kind of a more substantial bug fix or feature addition, we make a new release, and these are ordered in all previous releases, and we try to document what has been added. And so the latest version is version 1.11. And if you just download the zip file and unzip it, there's just an executable you run and it will run our software. So that's how you get the software. Okay, so now you can modify the code, you can build it to run in Linux, and there's some documentation that other people have written to do that. But most people, I feel, use Windows, and that's at least what it was developed under. And the idea behind the software is we would like to support as many new modifications and changes without having to go in and modify the code and recompile it. So a lot of the software is built around JSON files, which are like human editable files. And so, for example, all devices supported within the Miniscope software are kind of defined in this text file, this JSON file that we can edit. And so while 99% of users don't ever have to go into this, let's say we want to support the version 4 with this B&O head orientation sensor. All the features and communication for this device are defined here. And what it means is that if, let's say, you were going to build a version of a Miniscope with a different image sensor or make some other modification, oftentimes you don't have to modify the code at all, and you can add a new device and follow the kind of the format we've used to define, webcams or other Miniscopes here, and then like add a new device. We do this a lot. It's sort of like, for us, when we're building new things, it used to be that we had to go into the code and recompiling hard code new things to support a new device. And now we have this large field of view Miniscope, and we just add the configuration information here, and it now runs that. But for most users, you're generally not going to have to deal with that. But what you will use is when you download the software, there's this file called user configs. And in these user configs, this will define all the aspects of your experiment. So we have this kind of primary user configuration example, and it has a ton of comments that sort of anything that starts with comment tells you what these values are going to do. You can define where the data is stored. You can define the data structure. You can enable certain features. You define what devices are connected. You can connect a single Miniscope or a single behavioral camera or 10 Miniscopes and 10 behavioral cameras. It's been tested up to like 6 or 7 simultaneous video streams. But those are all defined in this file. So for your experiment, you will edit one of these user configuration files, and that's what configures the entire interface when you run it. So this has a lot of comments, and it's a good thing to kind of look over when you're first setting it up. But also, when you get to download the software, it comes with some example code. So this example code is just running a V4 Miniscope and a webcam. Has a little bit of comments, and it shows you what is defined, how to define that interface to connect to the devices you're using. So for our case, we will first connect to a Miniscope. So I have a Miniscope and data acquisition board sitting next to me. So I'm going to connect that to the computer. Hopefully it works when Zoom's running. And I'm going to start the software. So it's just an executable file in that zip folder that you unzip. When you run the executable file, the first main screen shows up. And this will tell you a bit of information about the current version of the software you're running, what devices are in that device configuration file that the software currently understands and can support. The software is also able to do video compression, both lossless and lossy video compression of any one of your video streams, and you can define a different video compression for each of your video streams. So for actual Miniscope recordings, kind of single photon neural imaging data doesn't do well with a normal lossy video compression. And this is outlined in some documentation. So for Miniscope streams, we usually use the gray codec, which is effectively no compression at all. Or we use this FFV1, which is a lossless compression, saves you on the order of 50% of the raw data size and doesn't actually lose any data. It does take a little bit more computational power. And so depending on the computer you're running, the number of video streams and the type of compression you're doing, you will want to make sure that you're not overloading your CPU for different video compression. There are cases where certain computers won't support some of these compression codecs, and they'll be listed here. So if we want to now load up our user configuration file that defines what devices are connected and all the where data gets saved and so on, we can select it here by just clicking select and going and finding it. But inevitably, what ends up being more useful is to just drag and drop. So I wrote this one recently. This is loaded up. This is the user configuration file we'll use right now. So I can up here define where the data gets stored and the structure of the internal folders. And you can add additional entries if you want to add additional information in how you store your data. And then effectively under the devices area, I'm going to define what types of devices I'm going to be streaming data from. Again, you don't really need to know any of this. You can start with an example file and then just modify it for your needs. But in this case, we're connecting a Miniscope, and in here, we're defining some of the default parameters, and you could leave most of this blank, but you might want to pre-configure it so when you load it up, it's using the settings you used last time. We define the compression and kind of initial values for like the tunable lens or LED and so on. But it's a pretty simple file, right? So if I drag this, I drag this into the main screen, I can just start running it, but I also have the option to look at all of these values in that JSON file in a kind of more maybe nicer interface. And I can edit any of them. So I can see that under devices, I have one Miniscope named Miniscope 0 and the parameters that are set. And I can always go in here and like edit these parameters. And when I load up the code, it will load up that way. Things that are like on or off, I can just toggle here. And it gives a tooltip for pretty much every one of these entries. So if I click on any one of these values, there'll be a little tooltip that tells you what it does, proper values for it, and so on. Okay, and you could, if you didn't ever want to go into actually like editing the JSON file, you could just load up a default one, edit here, and then save the configuration, and it will generate that file for you, right? So you could just completely avoid the text version of it if you want. Let's say we're happy with all of this. We're going to click run, and it's going to kind of load up an interface that's defined by that configuration file. In this case, I defined it as having one Miniscope, so one window showed up. And this is actually my Miniscope running. I can see light. And so some of the features on the screen here, there are these interfaces that support whatever configurations the specific Miniscope supports. So if I'm using a version 4, I have ability to adjust focus, excitation light, frame rate, and gain. So if I shine this on, with enough excitation light, everything fluoresces. So I'm going to shine this just on a piece of paper I have with some pen marks, and I can adjust the focus, which let me see if I can get something in focus. So now that this is very bright. So this is just the surface of some paper that I'm angling the Miniscope. So some of it's in focus and some of it's not. If I go to the tunable lens slider, I can adjust the slider and adjust the focus roughly plus or minus 150 micrometers. I can also change my frame rate. And as you can see, as I drop the frame rate, the image gets brighter because the amount of acquisition time per frame gets longer. And we can see the instantaneous and average frame rate up here as I change it. And it can go all the way down. I think we've written it to 2 frames per second, which is some specific person wanted that low frame rate. You can also change gain. So this kind of amplifies the signal within the image sensor. And people kind of go back and forth as to what gain is best. So this Miniscope is, as I said before, like 10 or 15 times more sensitive than the version 3 Miniscope. But you also want to always avoid photo bleaching with your Gcamp in the brain region imaging. So you want to use as low of excitation light as you can. And oftentimes that might mean changing the frame rate if you want, or changing the gain. So gain can effectively multiply the signal by 2 or 3.5. And if you go to a higher gain, it means we can decrease the excitation light, right? But the image gets slightly noisier because we're amplifying some of the noise as well. So there's trade-offs between the two, but the main goal is you want to avoid photo bleaching. So for however long you're imaging for, You don't want to see a significant decrease in brightness of fluorescence when you do it. There's also these alpha and beta channels. Now, this doesn't affect any data that's actually saved. We just directly save the raw data that's coming out of the Miniscope, but it can help for visualizing cells. And there's two ways of doing this. So first, let me turn this down again and find something kind of interesting. Not the most interesting, but some part of the paper. These can sort of change the dynamic range the software is just visually showing. And so oftentimes when you're imaging neural activity, you'll have sort of like this baseline fluorescence, that's just this overall brightness that's not really helpful to see. And if you change the beta value higher, it sort of it sets the dark level to a higher value. And the alpha value is kind of the opposite, right? So it changes what pixel value gives you totally white. And that can be helpful to see smaller dynamics of cells when you're imaging, right? This is an old Miniscope. So it has an issue that's solved on all newer generation Miniscopes. And it's something we haven't really mentioned yet, but on the side of all version 4 Miniscopes, and really every Miniscope we're now making, has this chip we call an absolute head orientation chip. And it's able to stream head orientation or orientation of the Miniscope in real time with the data. And this is visualized in the little Miniscope symbol rotating. This one has this old issue where this data sometimes gets corrupted, and when this little exclamation point shows up, it means that the data of head orientation is not great. Again, it's solved in new data. But if this is enabled, new Miniscope, if this is enabled when you record your data, you just get head orientation for free. Final things is as you change anything, it gets shown in this little control panel. And some of the like other modifications you might want to do, like, oh, you maybe realize you wrote the wrong animal name. You can go in and edit the animal name here, and when you start recording, it will save that data in with this new data structure. So we'll just do a very quick recording, and then we'll show a more interesting example. So I clicked record. It shows where the data is being stored. It's going to record until I stop it. And that's effectively the Miniscope software. I'll show the other features in 1 second as well, and we'll exit out of it. And if we wanted to see the data structure, I go into documents. In this case, I told it where I wanted to save it as in. I think I don't remember Miniscope. Today's date. Did I change this one? Hold on. Let's see, Miniscope, and then animal ID. I think it's. Did I do something wrong? I don't know. We'll save the next set. I'm sure I did something weird. Oh, I changed animal name. There we go. Yeah. Okay. Sorry. While it was set here, I changed it in the software, so it changed the data structure. And so this is our data. So it will save in a metadata file all the configurations that it used when reporting the data. So the time the recording started, but also where data is saved and all these other parameters. And then if I go into the Miniscope folder, I have the short video that was recorded. I also have metadata for this specific Miniscope, so all the parameters it was set for when we recorded it. And then timestamps. So the acquisition of every frame of any video source gets timestamped in milliseconds, and it uses the timer within your computer, which generally has an accuracy of about a millisecond. So there's a little bit of uncertainty in the timing from when a frame is actually acquired in the Miniscope for that data to make it to the data acquisition board, get packaged for USB communication, sent to the computer, acquired, and then timestamped with the computer timestamp. That's to say that it's generally within about a millisecond of accuracy. So these are the frame number. And if you look at the timing between any of these two frames, we're, I guess, running at 20 frames per second. It's basically 50 or 51 milliseconds per acquisition. If you needed a more precise timing down to microseconds level, the Miniscope data acquisition board itself, when you record, outputs a signal that toggles on every frame acquisition, and it's accurate to a couple microseconds. Okay, so that's kind of not necessarily the most interesting thing looking at, oh, Miniscope. I'll show one other thing. So one other motivation for using this newer version of the software is it should be a lot more reliable. So for things like running your Miniscope through a commutator, there's some commutators, like a specific one that was built, that might run for hours and never have any connection issues. But internally, a commutator really is a physical connection that's spinning. And as I mentioned before, there's cases in which the type of data we're passing through these commutators, the commutators aren't actually really designed for. So it can once in a while like drop a tiny bit of data, which ends up losing a frame. And so we tried to make the software be able to recover from kind of every disconnection and reconnect to the Miniscope. So this can happen in a slightly unstable commutator. It also means that like I can, so we have the Miniscope running now, and I can just unplug the entire system. So I've unplugged the USB cable. It's detected that we've lost signal, but if I plug it back in, it will attempt to try to reconnect to the Miniscope and reconfigure it to the same setting, right? So it can do this if the cable becomes loose. It's quite nice in that way. Okay, so maybe more interesting example is there's sort of like this hidden feature in the software that lets you play back previously recorded data, and we're just going to do this here since I'm not going to run a mouse in my house. So in this case, I've enabled a few more features in the software. I have, you can imagine this as imaging around retrosplenial cortex through a cranial window using a V4 Miniscope. So this would be the raw data streaming out of the Miniscope. We also have the behavior. I sped it up a little bit for this case, just a little bit more interesting to watch. There's also something in the software called a trace display window, which can display the traces of the head orientation, or if you've enabled Deep Lab Cut Live, it can plot the position of any specific joint from Deep Lab Cut Live into this trace. For our case, we're going to plot some cell dynamics. So I can click add neuron ROI, and I can just try to draw them on top of where our cells are. And it will add up to, I don't know, 32 or 64 channels or something, plots. But oftentimes it can be hard to see some of the dynamics if you're looking at the raw video, right? So I mentioned before, we can try to adjust this alpha and beta channel to kind of decrease the dynamic range we're looking at. But the software also enables kind of a rough real-time delta F over F conversion. This effectively is in a moving window, calculating what sort of the baseline fluorescence is, and then modifying, sorry, it's my wife's computer. And then modifying the display to show the percentage change of fluorescence. And this is really helpful to see, visually see what's happening by eye. Again, the data never gets modified when it's saved, it's still the raw data. We also have this show saturation button turned on, and it shows any pixel that's fully saturated turns red, which you generally want to avoid. Delta F over F, it's a little less meaningful. And so we can see these traces. So let's add a few more. And then in this trace window, we can zoom out a little bit and increase the dynamics. And so we'll be able to see calcium dynamics in real time on this trace. Now, when you want to record, like in the behavioral video, we definitely don't necessarily need to be recording these people putting reward at each end of the linear track. So we can select an ROI, and this will define what region is saved. And we can, if you want, you can do it the same thing for the Miniscope recording as well. And again, we can record. Another nice little feature is, let's say something happened behaviorally in your recording, you can take a note. And when you submit the note, it will get timestamped and saved along with all the other data. We can also hit spacebar, and maybe spacebar only works when we're not recording. If you're not recording and hit spacebar, It should say that we're I don't know, I did something wrong. It should also take screenshots with the spacebar, which it's not wanting to know. Anyways, okay, so let's say we did this. We can go back to stop our recording. And again, let's look at the data structure. In this case, I think I named it this. Here, there's this notes file. We took some notes. And so it gives us the timestamp in milliseconds from the start of recording that I took the notes. So 10 seconds in, 13, 15 seconds in. And then again, we have the same data structure for every device connected. We had a Miniscope 1 or 0 and the behavioral camera 0. And it has the video recording, but trimmed to the ROI we set, as well as all the metadata that came with it and timestamps. I will point out one last thing, which is a question that comes up quite often on our Google group, which is that all videos that are saved get saved at a playback frame rate of 60 frames per second. And what some people want to do is just use the playback frame timing to define the per frame acquisition timestamp. And we set it to 60 because no one generally is recording that fast, and it's noticeable that it's wrong. Because you'd never want to actually use the kind of whatever the playback frame rate is to define when each frame was acquired. Instead, you always want to, whatever analysis you're doing, take the acquisition timestamp file and use each of these timestamps for each frame as the timestamp for when that frame was acquired. That's because while like the Miniscope and Miniscope behavioral camera, Minicam, are kind of very accurately acquire data at a very whatever you set it to, very accurate frame rate, data can be dropped through a commutator or through the USB. And if you lose a frame, that will show up in the timestamps, right? If you lost a frame that never arrived to your computer, that frame just never arrived. And so the timestamps will still be correct. Whereas if you just were looking, averaging the number of frames you had over the length of the recording of the video, you will get slightly off in certain cases. So always use timestamps and never the actual embedded timing of the video. I think that's it. I didn't show Deep Lab Cut Live, but part of what's built into the software, it just runs Python in the background. And so you can actually run user-defined scripts. In our case, it runs Deep Lab Cut Live, and it can also, there's a version that kind of alpha version that runs Sleep, a different kind of machine learning social animal tracker. But you can also theoretically write your own Python scripts to run alongside the acquisition and saving of data. So I think with that, I will stop sharing since we have a couple minutes before we move on, if there are any questions. Which parameters do you move to see the trace window? So you enable the trace window in the user configuration file. There's an example in the software. And then you can click or drag and click to select cells or regions in your recording to plot them in the trace display. And then I didn't show it here, but the controls are listed in the control panel. They're like the scroll wheel, and holding control and scrolling will change the time shown and the scale. You can also double click on a trace and on an individual level, change the scale of any individual trace. Again, it'll also plot head orientation and even Deep Lab Cut positions, and that's all defined in the user config file. If you run Deep Lab Cut Live, it opens another window showing the video stream for Deep Lab Cut Live, and you can define what joints you're going to plot on top of it. It also will show a heat map of the time spent across the environment you're recording from. How do you find a dropped frame? So again, depending on the coax cable, commutator, USB, our system is sort of jamming data over USB. If your computer, for whatever reason, for a moment can't handle that rate of data and drops a packet, you will effectively lose a frame. The software will show in the top right corner, top left corner, whenever a frame's dropped, but it's really not an issue, right? So we probably average like for a 10-minute recording, using maybe dropping 10 frames on a standard Miniscope configuration, those frames will just like, you effectively don't worry about them, right? Because they are, they just never show up in the computer. And so there will be an interframe interval that's twice as long because a frame in between it was missed, but all the timestamps are correct. And it's really not an issue. We display that number because let's say your commutator was very faulty, or like the connections of your coax cable were loose. If that dropped frame is increasing very quickly, you want to fix something. But in general, a couple dropped frames every minute is no problem at all. I think, what is the bit depth of your camera? That'll be the last one. Answer, because we use this USB video class USB data protocol, on Windows, it just supports 8-bit depth. Our actual Miniscope image sensor sends out 10 bits, and we could send out up to 12 bits with other image sensors, but we drop that down to 8 bits by the time it makes it into the software, because that's just what's supported by the standard. This is really not an issue for any of the types of imaging you generally will be doing. A single cell ends up occupying tens to like 100 pixels with its fluorescence. And the analysis approaches, which we'll talk about tomorrow, effectively can use that data that's spread out across pixels, and you end up getting much higher bit depth because you're kind of averaging these signals across multiple samples of pixels. But it is one reason why we are working towards also moving to other USB protocols where we're not confined to like 8-bit. And for certain cases, we might want to send generic data or 12-bit imaging data. But it really, at the moment you go over 8 bits, you have to double all your file sizes because you have to save everything as a 16-bit value. It's just not worth it. I will try to answer these other questions in chat while we move to the next session, which is talking about imaging, in vivo imaging and behavior with Will, Joe, and Zach. And if you have any remaining questions, we are all around the hour after this next talk in breakout rooms. So you feel free to jump in and follow up on any of these questions I don't make it to. So with that, we'll hand it over to Will, Joe, and Zach. Oh. Are you guys able to connect?
Do you guys see anything?
We just see that you've started sharing, but it's a black screen.
Okay.
I guess while they're trying to figure that out, I can try to answer a few more questions. There's a question with the V3, they only had a good results once with an expensive USB cable to the box. Cheap cables don't work. So this is there's a couple like common issues that show up. One is not all USB 3 cables are equal. So you don't necessarily need an expensive one, and we outline on the parts list the USB cables we use, but there is there can be an issue where like some USB cables aren't actually USB 3 cables. So if you're having issues with connections, it's generally try to swap out the USB cable. Try just to debug things, a USB 3 port on another computer. And then the main source of connection issues are usually an issue with the coax cable. So if the coax cable connector isn't soldered well, or becomes loose, or generally gets damaged, that's almost always the major source of issues. Okay, now it's working, Joe. So I'll stop there, and again, I'll answer more questions in the chat.